Hello everyone, welcome to week 8 of this course. So in this week we will start discussing about the new paradigms, instruction fine-tuning and RLHF that have shaped the field in the last few years. So this lecture I will start discussing about instruction fine-tuning, what is this paradigm, and we will continue this for another lecture to see more about various aspects of instruction fine-tuning. So we'll talk about so we'll start discussing broadly on given a language model that we have learned how to pre-train, how to fine-tune, how do you make them align with human intents, and this will give us motivation to talk about instruction fine-tuning. And we'll define what is that and what typically do we do in instruction fine-tuning separate from what we have already learned, right? So we have talked about the pre-training fine-tuning paradigm, and we have talked this in detail in week 6. So what happens? So you have a language model, so it can be transformer typically. You can pre-train it with a lot of data, and then once you have pre-trained it, you have a very good initialization, and you can now fine-tune it for a new task, right? And so you can fine-tune the same model across for new tasks, right? And what you do, you give the input and the output and let it tune its weight so that it can predict the particular output given an input. Now even with that, I mean we went up to GPT-3 in discussing the pre-trained models. So people said, okay, are the language models able to follow human instructions, and how often do they do that, right? So suppose this is the prompt that somebody gives to a GPT-3 model: explain the moon landing to a 6-year-old in a few sentences. Right? Now what would you expect? You would typically expect it to actually explain the moon landing, right? But what GPT-3 gave output is explain the theory of gravity to a 6-year-old, as if it was trying to create sentences similar to what was the prompt, right? In different scenarios similar to the prompt. Explain the theory of relativity to a 6-year-old in a few sentences. It was creating similar sentences because maybe in its pre-training data it had examples where after an input you had some variations of the same type, right? So it was creating this. While a human, so they are not aligned with user intents. While a human would do this, human will actually start explaining a giant rocket ship blasted off Earth carrying astronauts to the moon. The astronauts landed their spaceship on the moon and walked around exploring the lunar surface. Then they returned safely back to Earth, bringing home moon rocks to show everyone. I mean, that is one way you can explain it to 6-year-old, right? Now, how do you ensure that the language models are able to follow this, right? Now, similarly, incorporating human values. So you may train the models for doing the next word prediction task, right? But let's say you give this prompt to GPT-3. It is unethical for hiring decision to depend on gender. So this is something that you wanted to follow. Therefore, if we were to pick a CEO among Amy and Adam, our pick will be. So it answers Adam. Maybe it can answer Amy also, right? But what will a human answer, right, in this particular scenario? Now, the human will typically say, okay, fine, you give me more information. I don't have information about their background, their qualification. So how do I choose them just based on genders, right? It's okay, I will not make my decisions based on genders, but I need to have their background information, right? So human will say neither, as we do not know much about their background or experience, right? So yeah, again, how do we make language models incorporate human values? And this is what I mean. Haskell's definition of alignment says that AI is aligned if it is helpful, honest, and harmless. Now, this is applicable to all the language, different type of languages, even about doing with audio, speech, text, so on, any other modalities of communication. Now, so that brings us to this question that, okay, so we talked about pre-training, we talked about fine-tuning, but what else do we do to make language models aligned with our intentions, like or make them follow our instructions properly, that we are articulating in language, right? So we are giving it in language, and how do we try how do we make them align with our intents, right? So now so we talked about this very briefly, this training this GPT assistant pipeline, um, and we have covered this part pre-training already. Now what we will be covering for understanding how to make them as an assistant are the next phases. That is, first we do supervised fine tuning, but it's different from the fine tuning we talked about. Okay, so this is what we will study as instruction fine tuning. So how do we do instruction fine tuning on these models? And now once I do instruction fine tuning, how do I do some RLHF, right, or preference modeling? So this is the RLHF phase that we will talk about. So this will be the main focus for this week. So how do we do instruction fine tuning, and how do we do RLHF starting from a pre-trained model? Okay. So typically, as you can see, we will start from this base model, and that has been pre-trained, and we will do instruction fine tuning. The good thing is that pre-training already has learned a lot about the data and the world, because it has got some trillions of words. But here I want to be focused, so I'll give it some specific demonstration that will be much smaller in quantity, right? And this number of days I need for instruction fine tuning training is much less than what I need for pre-training. Okay. So then, what exactly is instruction fine tuning, right? So let's try to understand that from some very basic examples. So how do humans learn, for instance? Right? So this is an example from you can say KG and first, right, type of notebook, and the task is that you have to count on by tens to add. This is the task instruction given, then fill in each blank, and you are given how to do this, right? So you have to do 41 plus 20. What you do, you add 10 to 41, you go to 51, again add 10 to 51, you go to 61, right? And now you are given actual tasks. So you are saying 52 plus 20. So you have to now follow this particular example that is given. So count on by tens to end, then fill in each blank. So I say 52 plus 10, 62 plus 10, 72, right? And I fill 72 here. Similarly here, 65 plus 30, 65 plus 10 plus 10 plus 10, 95. I fill 95, right? So what do we see here? So you had task instruction, that is how do you count and where to fill, and you had very few examples. So you had just maybe one example that was sufficient for you to learn how to do this task, right? And that's where we are going. We are saying, okay, I give you one example on how to do this task, and you may possibly learn how to actually perform this. So now typically when humans learn, this is the way they do. I mean, they get detailed instructions, right? And very few examples. We don't need too many examples for learning things, right? So a detailed instruction, how to do this, and some examples. While in machine learning, what is done is you learn a mapping from input to output, and you depend on the data. So you need a lot of data to learn this mapping, that from input to output, and you don't care about instructions in this learning paradigm, right? So there is no instruction here. You have the input and output, and you want to just learn this mapping. So instruction can actually help the model in saying, okay, this is the task, right? So it will say, now this is the input, and give me the output. So the instruction here can actually help. So if I put the instruction before the input, this can actually tell the model how to do the task, right? I mean, otherwise you have the input, and you are not even telling the model how to do the task. So it just learns from a lot of data how to convert input to output, and just uses that for a new input, right? But if you give the instruction and maybe give an example that this is how you do the task, the model may be able to do the task, right, with very few examples. And that's the paradigm of instruction fine tuning, that you give instructions, and the instructions will enable the model to learn how to go from input to output. Okay. So while the mainstream machine learning will be no instructions and large training sets, and maybe even like sometimes you use hundreds of examples, even you do fine tune pre-trained models like BERT and so on. So, so then how do you transit from say a machine oriented the machine learning models that we typically use to providing human oriented instructions, right. So, that is what we will discuss. So, you pretend that the machine is human and you start providing that task description, like here you give it as an input to the machine that given an utterance and recent dialog context containing past 3 utterances, output yes if this happens, no if this happens, and then you give some example, positive example, negative example, right. And then let the model, given a new input, let the model produce the output. Right. So, you are describing what the task is about, you are explaining the task, you give an example, and then can it help the model to do the task, right. Oh, so you see, I mean, you can make a parallel between this and what we have seen. So, you have some example, one example, and you had instruction, task instruction, right. So, this is how humans learn. So, can machines also learn in a similar manner? So, the basic premise though is that okay, I am describing everything in natural language, but are machines good enough to understand natural language? And that is the premise. With all this pre-training, they have seen lot of data and they have some understanding of the language, right. I mean, they can, given the words, they can construct some representation, right, of what has been said till now. So, and then any task you can think of, you can then express it as in natural language, right. So, I want to do sentiment analysis, I can say is the sentiment of this movie review positive or negative, and you can just say this is the movie review. Or say what is the translation task, you can say translate a sentence, English sentence into Chinese, like that you can describe your task. So, that is the basic premise, that you can, any NLP task you can describe via natural language instructions. Now, why define task in natural language? So, Alan and I was one of the first group who started focusing on this, and what they mentioned is that the current paradigm of supervised learning is successful in building task specific models. They do not generalize well to unseen tasks. Okay. So, if I train a model to solve questions, it cannot solve the classification task. I will have to train separate models for solving questions and doing classification. But on the other hand, if we can make a model equipped with understanding and reasoning with natural language instruction, so if it learns how to follow an instruction to do a task, right. So, we have an instruction and a task. If we can make it learn, given this instruction, how to do this task. Now, for a new task, you just describe the instruction and the input, and it will learn how to do the new task, right, because it learns to reason from the instruction, right. So, and that should be able to generalize to any new task, and that was the main pitch, that by using this idea you can generalize to new tasks. Okay. So, now how is that a different paradigm? So, you can try to contrast it with paradigms like pre-train fine tune and prompting. So, what do you do in pre-train fine tune paradigm? You take a model and pre-train it on a large data set, right. Then you want to do sentiment analysis, you fine tune it on sentiment analysis, right. So, you need task specific examples, and you will have one specialized model for each task. So, you will have one for summarization, one for sentiment analysis, and so on, right. So, you can pre-train and fine tune on a particular task. While what we will do in prompting, you do not fine tune the model, you take a pre-trained model and give it the input, right. You can give few shot in the training, there is no parameter change that happens, and you can do inference, right. You describe your task in the input and you prompt the model. There is no fine tuning happening. So, instruction fine tuning is like a combination of these two, where what you do, you say okay, I have a pre-trained language model, I start from that, I do fine tuning, but while fine tuning I give instructions. So, I do instruction fine tuning on multiple tasks. So, not just on one task, I can do it for multiple tasks. I can take sentiment analysis, I can take text summarization, I can take question answering, multiple tasks, and I will give the instruction, I will give the input and let the model produce the output. So, I will train it in that manner, and then once I have instruction fine tune the model, Then I'll take a new task, right? A new task that has not been trained on, the instruction fine tuned on, and I'll try to give the instruction for the task and the input and let the model produce the output, right? And then I will see whether it can generalize to new task. So that's the paradigm of instruction fine tuning. Okay, so you'd fine tune, but with instructions, right? So that it learns how to reason with the instructions. Right? So now, what do I mean by instructions? I mean there are various different works, and they define it in some define it in a very complete schema, some define it in a very simple manner. So this particular work, cross task generalization via natural language crowdsourcing instructions. So they have defined the full whole schema for instructions. So they say, okay, you just have input outputs in the data, right? So these are your input outputs. That's what typically the ML models would use. But now, and you will have some number of instances. But now, let's say I append to this many other things, like a positive example about it. So input and output, positive example, and the explanation why this is a positive example. I can have a negative example, input output, and explanation why this is not a correct example, and a suggestion like what you should avoid. So I can provide some examples, the first thing to add. Then I can provide the task, what is the title of the task, define the task, what are things you should avoid, and emphasize, like what you should emphasize, what is your caution, right. So this can be my instruction schema, right. So they started with this whole instruction schema, and they defined it for many different tasks. Good thing was that many tasks already had the task that they selected already had these instructions, because they were created through human annotators. So when we give the task, when we create data through annotators, what we do, we give them detailed instructions that, okay, this is how you should perform this, say, aspect based sentiment analysis annotation, and these are some examples. So this is the sentence, these are the aspects, these are the sentiments, and that should be the format of the output. So we give them detailed instruction, and they were able to use the same instruction in their data set for instruction fine tuning models. Okay, so for an example, so this is the question generation task, MC Taco. So you had the title, writing questions that involve common sense understanding of event duration. You had a task definition that we ask you to write a question that involves event duration based on a given sentence. Event duration is defined as the understanding of how long event typically lasts. Like brushing teeth, you should have a common sense, some common sense way you can try to think how long this event will last. It will take a few minutes. Right. Emphasizing caution, like they are not required to have a single correct answer, because you ask this question to different people, they may give different answers. The thing to avoid is that don't create questions which have explicit mentions of answer in the text. So if the text already answers the question, there is no reasoning, common sense reasoning about event duration that is happening, right. So like a positive example, the sentence is Jack played basketball after school, after which he was very tired, and your output is how long did Jack play basketball. That means this is the question that you have generated. Now is this a good question for this task? Now you will need to do some common sense reasoning, like how long he would have played basketball because he was tired, right. So it's not directly apparent here. On the other hand, let's take a negative example. So he spent 2 hours on his homework, already given in the input, and the question is how long did he do his homework. I mean there is no common sense reasoning, you just retrieve from here 2 hours and you can respond. So this is a negative example. So we do not want the question as the answer is directly mentioned. And then you give a prompt that ask a question on event duration based on the provided sentence. You give a sentence. So instruction you will have instruction. So this is all your instruction, right. Instruction has everything, right. And then you will have an actual instance, right, task instance. So you have an instruction. So what is important? Instruction, input, output. So when you will do instruction fine tuning, what you will do, you will put the instruction and input as your input, right. I mean, so instead of input, you will have instruction plus input. So wherever, if you are using encoder decoder model, you can put instruction and the input in the encoder, and you will learn how to decode the output token by token in the decoder. Or if you want to put everything in the decoder, fine, instruction plus input will go as a prefix, and then you will start generating the output word by word. So here are some task examples, right? So you have the input and the corresponding question that you have generated, and use that to do instruction fine tuning. So what they did, so they had collected a lot of different kind of questions. So they had data sets on question generation, answer generation, incorrect answer generation, classification, minimal text modification, long text generation, verification. So overall 61 tasks with 193,000 instances, 7 categories, and they tried diverse reasoning skills like numerical reasoning, co-reference resolution, common sense reasoning, multi-hop reasoning across diverse domains like sports, history, news, conversations, and so on. Right? So they collected a lot of tasks from a lot of domains and a lot of reasoning skills. Now using that, they saw, what is the impact of this? So they contrasted this with multitask learning, where what you can do, the same thing. Let's say you have, say, leave one task, right? Leave one, or let's say leave one data set. So they have some data sets. So you leave one data set and you train on everything else. And then finally, when your model is trained, you give it examples from the data set that is left, right? And you test. And this like BART model fine tune on multitask learning gives around 37 the score. Instruction fine tuning, you will instruction fine tune on all the data sets except the one that you have left out, and then you try this much better performance, right? And then you say, okay, what if you leave one category itself and try to test on that, and this was better. You do random split of tasks, then also it was better. Leave one task, right? And they contrasted that with, okay, GPT-3 you give full instructions. So one thing was sure, giving full instruction to GPT-3 was doing better than multitask learning, right? But if you can actually fine tune the model, GPT-3 is not instruction fine tuned, but with instruction fine tune was able to outperform, right? And similarly in this setting, yeah. But supervised upper bound was when you fine tune BART on exactly that data set, right? When you do instruction fine tune, they were not fine tuning on the corresponding data set on which they were testing. Here they were. So that of course is an upper bound. You train it on that data set, you will do well in that data set, right? But you see, the difference was not so huge in these cases. It was huge in some cases, but not so huge in the other cases. Right. So that's what they found, that instruction improved the cross-task generation significantly. And even though BART is like 1,000 times smaller than the GPT-3 model, it's able to outperform. Okay. So that was something that they could see from the experiments. Now they also tried certain ablations, like what happens if so this is like the same model. What if they remove negative examples? So this is one thing that they found. If you remove negative examples, the performance was actually increasing. Okay, so that means, although this makes sense that for humans negative examples would help in learning that the problem, that you should not create such kind of examples. You should not perform the task in this particular manner. It's not so clear how you would make machines to learn from negative examples, right? Because typically they work with the attention paradigm. They can see, okay, how to put attention on something, but saying, okay, do not do something like this may not be so easy for the machines. So they found if they remove negative examples from the instruction schema, they typically do better, right? So they are very difficult for the models to learn with. Now they also saw, is there some scaling law? Like if I further want to improve performance from what I have achieved, what should I scale on? Should I get more instances per data set? Should I do more different kind of tasks? What should I do? And what they found, so this is with full instruction. So if you keep on increasing the number of training tasks, the performance improves. So the model is learning from number of tasks, and it is able to do better on some unseen task, right? And this gives a hope that, okay, if you can increase the diversity, increase the number of tasks, training tasks, the model may become stronger and stronger, right? Uh, while this was not happening with other things like no instruction, so this was not improving that much, right? And some way like prompt plus positive example, it was even decreasing. So, but full instruction actually was increasing, right, consistently. So, can we actually improve? So what they found, the cross task generalization, this improves with increase the number of observed tasks. So that's why they came from natural instruction, the first data set, to supernatural instructions, where they enhanced this data set. So they had 1600 plus tasks across 73 categories, 74 domains, 43 languages, right? I mean, so it's a huge task. I mean, very large group of people and institutes that did together, and they created the supernatural instructions. Okay, and you can see, I mean, they had variety of tasks. Translation was one of the major thing, question answering, program execution, text categorization, text matching, question generation, toxic language detection, text completion. They had a huge variety of tasks, 1600 plus tasks. Okay, and this is an example of in cause effect classification. So you have a coreference resolution and Vinograd challenge. So you are given a question containing a blank, and it has two options. You should pick the best option to answer, and please answer with A or B. That's the task instruction definition. You have positive example, the input output is B, and explanation why that is so. Negative example, explanation saying, oh, you cannot put in parentheses around the answer output, right? And then you have an actual instance. So valid output, right? So what would you do? I mean, you will put all that up to the input here in your prefix or your encoder and let it generate the output, right? And that's how you will fine tune it. So all the tasks you will have the instruction plus input, and you want to generate the output, and you simply do the next token prediction here. So the loss is not different. You still, the paradigm is same, next token prediction. Okay. What changes is what are you putting within the input? You are putting the instruction along with the input, right, to help the model. And they found that these were the two models that they developed, tkinstruct and the multilingual version of that mtkinstruct. So they found that so for English data set, it was able to outperform everything else. So 11 billion model with a 62 performance. Similarly, mtkinstruct was able to do much better in the cross-lingual settings. And the gap between this and the supervised, fully supervised training was also reducing. So here, of course, there is no supervised fine tuning, but here you can do so. You have done complete supervised fine tuning where you get better results for the task. So this paradigm actually became very, very popular, and they tried various ablations. So like what is helping, and I mean the good thing was that so if you just have a definition and two positive examples and training time, and definition and two positive examples at test time, this typically works well, right? I mean, so if you add negative examples, they don't add so much, is what they found, right? And everything else. So going forward, I mean, most of the instruction just became, you define the task. So you have the task definition, and you have some positive examples, and that should be good enough for the model to learn. Right? So that's one learning that we had from here. So okay, I mean, this was so we started talking about instruction fine tuning. So here, if you see the scaling laws were very similar. So if you increase the number of training tasks, the performance increases, right? If you increase the number of model parameters, the performance increases. So they went up to 11 billion model. I mean, and the performance was kept on increasing. So both are, scaling is important in both direction, the model size and the number of tasks. But if you give the number of instances per task, right? So I have a sentiment analysis particular task. If I have 10 examples right now, if I create 100 or 1000, the performance does not increase so much. So it's not actually improving from 60 to 600 instances per task. So it's not important that you have many instances per task, but what is important is that you have diversity of tasks. Okay. So that is something that they learned from the scaling laws. Okay, and chapter 12 of our SLP3 book talks about this, the instruction fine tuning. We will still continue with the instruction fine-tuning in the next lecture because there are many more details that are left. Okay then, thank you.